Claudia Gutiérrez from Barcelona. It is a great pleasure to have you here, Claudia. I first met Claudia in 2014. 15. It was
10 years ago.
10 years ago in Tenerife at Arribas. And we worked together in many few collaborations like Pesto, Pesto Plus, and the surveys that was its successor. At that time, she was working with Professor Mario Nui in Santiago at the University of Chile. Then I think you're quite a world traveler because you've been in many other places. You've been in Santiago up to 2016, but then you moved to the University of Southampton, working with Professor Mark Sullivan in the UK. Then you decided, why don't we go to Finland for she won a Finca fellowship, which is quite a prestigious fellowship, I would say, working at the University of Turku in Finland, in the sunny Finland. And then he said,
sunnier than the UK.
And then in May 2023, she decided to Barcelona.
Much sunnier.
I do believe that when you write a paper about Corcolab supernova, you have to cite at least one of her papers. So I think she made a great job with that supernova. But this is not the only thing that she's interested about. She's also interested in understanding the influence of galaxy properties on progenitor of stars, supernova explosions, observational parameters, and the origin of other peculiar extreme transits that surveys are discovering. So, Claudia, do you have, please, let's talk about
Okay. Thank you very much for the invitation. I'm very happy to be here. I'm surprised. I think some of you heard this before because I didn't expect to see the mountains. So I really love them, and with the snow, it's so beautiful. So thank you very much for the invitation. And I'm working, my focus is on supernovae. As Leonardo said, my thesis and many works were focused on hydrogen-rich supernovae. But today I will talk about the diversity of Corcolab supernovae, telling you what they are important, we need to care about them, and why they are so beautiful, as this picture that you can see from 87. So just to start, I will do like a general introductions to explain what is a Corcolab supernovae. So these are the final explosion of massive stars, and depending on the elements, on the layers that the star retain at the moment of the explosion, we have a diversity that you can see here in the left plot. And this is the way how we study supernovae. So we split them based on the lines that we see in the spectra. So if we see hydrogen lines, we call them hydrogen-rich supernovae, type 2. If they don't show the hydrogen lines, they are stripped envelope, all of them, or hydrogen-poor supernovae. So all these three groups down here, they are stripped envelope. If we go without hydrogen, we have just a spectrum dominated by helium. We call them 1b. If there is no helium, no hydrogen, as the last one here, we call them 1c. However, there is a type that is a transitional one between a hydrogen-rich and hydrogen-poor that is called type 2b. So the 2 is coming from hydrogen, so it was hydrogen-rich at the beginning, and we can see some hydrogen lines early in the spectra. But as time passes, the spectrum gets dominated by the helium lines. So that's why it goes with the B. So this configuration, this diversity in the spectra is telling us something about the progenitor star. So if we go to the plot in the right, we can see that we have this kind of onion-like structure where you can have like the external hydrogen envelope, the star retain that. So you see the hydrogen lines, and then if you remove some of the layers, so this hydrogen decreases, so you have the type 2b, that is just a small shell of hydrogen, but then you have like whole full helium and other elements below. If you don't see neither hydrogen and helium, so it's a very stripped star. So this is telling you that is a kind of mass loss, but how the star is losing this mass, we don't know exactly, but there are some approaches that we can explore to understand this process. So this here, I summarize the picture, the classification picture that we have around 98, more or less, where we have objects having hydrogen, type 2s, without hydrogen, type 1, and then the subclassification. The thing is, in the 90s, we have two new types that appear. So in 93, some people start to see some narrow lines in the spectra of the hydrogen-rich ones, and they name these objects type 2N, and the N comes from narrow lines. So that was the name. And the idea is that these lines are narrow and in emission because the supernova ejecta is interacting with CSN, with circumstellar material. And in 96, 97, 98 was another type that is 1C broad line. So basically, it's a spectrum of 1C. So no helium, no hydrogen, but the lines are very broad. These are the introductions that we have in the 90s. But let's go to the open questions that we still have in the field. So what about the progenitors? So we know they are massive stars, but we don't know which kind of star they are. What is the explosion mechanism? All of them explode in the same way. How they lose mass because of a companion, because of the mass loss. What is the role of metallicity? And finally, what are the environments? So in which kind of places supernova explosion? So to explore all these open questions, we have different approaches, and let's go to explore the progenitor. So the direct way to explore the progenitor is by identifying the progenitor in pre-explosion images. So this is the only direct way that we have till now, but it's very constrained because we need a supernovae to be very nearby, between 25 megaparsec. So we need nearby objects, that's one. And second, they have to be nearby, but we need pre-explosion images. So we need that before the explosion, someone were taking some images, deep images of the field. And the way how we identify the progenitors is the following. So if we go here to this top panel, we have an example with the supernova 2008 BK. This is a type 2, so hydrogen rich. In the B panel, we see the object that is very bright. So this image was in the peak luminosity. But then if you go back in time, people realized that were an image of the field. This was with BLT, but is normally done with HST because it has the resolution to resolve individual stars. But in this case, the object was very, very nearby. So with BLT, they found that they have these pre-explosion images. So they look for the position and they say, okay, we think that this red star is the progenitor. So at that moment, that was the progenitor candidate. What do you need to do to confirm if that is the progenitor? You need to wait 2-3 years when the supernova disappears to see if there is something in the location. So they wait. This is from 2010, sorry. They wait, and like 2 years later, and they didn't find the star that was here before. So they said, okay, we confirm this object, this star as the progenitor. Using this technique, we have identified around 20 progenitors for type 2. So this is the most successful one. Well, also because type 2s are the most common type of supernovae in the nature. And most of the progenitors are red supergiant stars. But when people start to analyze all these progenitors in a statistical sample, they found that the masses of the red supergiants didn't exceed like 20 solar masses. And that was a problem because based on the observations in the Milky Way, we have red supergiants that go up to 25, 30 solar masses. So they call this the red supergiant problem. So we are now finding red supergiant progenitors more massive than 20 solar masses. Now there is a big debate here if there is indeed a problem, so if there is a missing population, or if we have some problems, for example, estimating the extinction, that is a huge problem in our field, or if we need maybe more colors to have a more precise information of the star. Even other works claim that more massive red supergiants, they continue the evolution, so they are not the progenitors of type 2, they are the progenitor of strip supernovae. So this is the most successful way, and for type 2s, we have, let's say, a good number. Now the problem is for stripped envelope. So for type 2Bs, we have identified 5 progenitors, and at least 2 of them were like consistent with yellow supergiant progenitors. In some other works, they claim, okay, we need them to be in binary system. For this, we have 5, but there are also debate if there is indeed these stars are indeed the progenitors. But let's say they have some confirmation for yellow supergiant, so that's good. For 1B, so this is the helium-rich ones, we have one candidate that was consistent with a blue progenitor, and the conclusion in this work was, okay, if we have this progenitor, is probably, or was probably in a binary system. And now we have 2 1Cs, just candidates, that one is consistent with a very massive progenitor, and the other one with an inflated progenitor that is in a binary system. And this one, I checked last week, and for 2017 EIN, they said that the candidate was wrong, so they are still looking around what is going on there. But here, this is the example for the 2019 object. This is an HST image. On top, on the left panel, you can see the supernova at peak, and then you go back in years, you find the place where they explode, and this is the candidate. So even though this is the best way to do it, it's limited because we don't have many supernovae nearby, and most of them are type 2s. So we don't know how the progenitors are and if they are in binary system. But there are another ways to constrain the progenitor, and one of them is like modeling. So you can model the light curve, and here we have 3 different examples. Modeling the light curve using, for example, hydrodynamical models, you can constrain the progenitor mass, the radius, and the kinetic energy. So the kinetic energy you constrain at the beginning thanks to the expansion velocity, so how fast the ejecta is expanding, and then you start to play, let's say, with different progenitor masses and radius. So on the left, you have an example for a type 2B supernovae, so these transitional ones, that in some cases, they have this double peak light curve. In the middle panel, we have also a double peak 1C supernovae that have progenitors consistent with helium-rich star. And in the right panel, we have, this is a subset of more or less 50 supernovae that we analyzed in 2022 for type 2s. So from this, as I say, you can get the mass of the progenitor, the radius, and the kinetic energy. But you can also do it with a spectral modeling. So if you compare your spectra with models, you can also constrain metallicity, radius, kinetic energy. That's early on. But with late spectra, in late spectra, you see emission lines, you can constrain the mass of the progenitor. What's the problem? The problem is that we have few models, and this is very expensive to have, like for one supernovae, to have the full evolution. So the thing we do is like comparison. So for example, in the right panel, there is the supernova 2015 BS that is in blue. And then we have 2 models, one with 15 solar mass and the other one 25 solar masses. And when you see the field, you say, okay, my spectrum is between these 2. So the mass of the progenitor is between 15 and 25. That is the best thing we can do now because there are very few models. But this is a good way to approach and to have the progenitor mass. But we can also start the environments. So the environments can tell us where these stars live, evolve, and how they explode. So we have the work two examples. There are many more works, as you can see here. This is from Galvan, 2018. He was using IFS data, telegraph field spectroscopy, and analyzed a sample of more or less 100 objects. And the conclusion, at least for core collapse, is that 1C, so hydrogen-rich, hydrogen-poor, helium-poor supernovae, they have higher progenitor mass. They are in metal-rich environments. So if we stop here and think a bit about this finding, they are consistent. So if a metal-rich environment, if a star is in a metal-rich environment, the mass loss is more efficient. So it's easier to remove the outer layers. And if it's a more massive progenitor, again, the mass loss is more efficient, so that these results are consistent, but they are also in higher star formation rate. They have also higher star formation rate, the places where they are. So all this makes sense, and it's consistent with a stripped supernovae. Now, the important thing maybe from this work is that they found that type 2b are in metal-poor galaxies. And this is from this plot in the middle, where we have the oxygen abundance, that is give you an idea of how rich is the environment. And type 2bs are in orange here, and they tend to be in lower metallicity. So this result is important because if a star is in a low metallicity, and we believe that metallicity is playing an important role in mass loss, so the mass loss is less efficient. And we expect to have here probably type 2s, that you have a hydrogen envelope, but they are losing some mass. So maybe these objects at low metallicity are in binary systems. So this one from here. More recently, it should analyze the PTF sample, the Palomar sample, and they didn't distinguish between 1B and 1C, because to do this distinction, you need like a good spectral data, and they don't have much for that. But they said, okay, they are in more massive galaxies. That is also consistent with that. So more massive, metal-rich, easier to find the external layers. And in type 2b, they said type 2b explode in similar galaxies of type 2. So maybe we are just going here, and we are missing some type 2s at low metallicity. Another way that we can analyze and understand the progenitors is by analyzing the evolution of the objects. So in 2014, we published the analysis of a type 2, so hydrogen-rich supernovae, and we show here, these are the light curves, so the brightness against the time. We see a large diversity in the luminosity of these objects. So they have a high diversity in that, but also in the morphology. So we see that some type 2s, they evolve very fast, decay very fast, and another ones have a constant luminosity or quasi-constant luminosity for a few months. Before this work, the idea was that type 2 fast declining, that we call type 2L, and slow declining, that we call type 2P, because of the plateau. They were like two different populations. But with this, we show that they don't. They show a continuum, and the progenitors are coming probably from the same population. And then we, 2-3 years later, we proved this also spectroscopically. So we analyzed the spectra of type 2, we compared different parameters, and we found a continuum. So right now, when people analyze type 2 supernovae, they try to avoid the subclassification type 2L, type 2B, because we saw this continuum here. For a stripped envelope, there are also many studies. There is also here in the references. And they normally, when you study them, you study like as a group. And from the spectra, LU in 2015, they found that there is a continuum between the properties of type 2B and 1B, the transitional object and the helium-rich. And Chivers in 2018 found that the velocities for 1C are higher. So if we go here to this plot, we see the expansion velocities as a function of time for the different subtypes. And we found that the 1C, indeed, they have higher velocities. But there is a continuum. So they have higher velocities, but it's difficult to say if it's one class of the other one. If you go to the light curve, in the light curve, you also see it has huge diversity, like in this one, in terms of luminosity. But in Tadia's work, they found that they have similar light curve properties. And later, before in Lyman, they analyzed the properties of the explosion mechanism. So they analyzed the nickel mass in the right on top, the ejecta mass, and the kinetic energy, and they found that 1C and 1B, they have similar distributions. So the colors are blue 1B, red 1C, and they have similar distributions here. So it's difficult to distinguish. And the conclusion is that they have similar progenitors. Now, the difference is when you have the 1C broad lines, that we said they have broad lines, and this is like high velocities, and high velocities translate to high energy. So you can see here they are more energetic explosions. So with this, it's difficult to disentangle between the 1C and 1B progenitors. Now, for the type 2N, that they are hydrogen rich but interactive, again, there is a huge diversity. It's always a huge diversity everywhere. In luminosity, so we have all these objects, but by eye, you more or less can split this into populations. One that evolves very fast, that they call the fast risers, that they go to the peak in about 20 days, and again, they decay very fast. And the slow risers, that they go to the peak in around 50 days, and the decay after peak is very slow. All of them have narrow lines in the spectra, but the diversity is bigger in the light curve because they didn't have a spectral sequence for these objects. So they didn't know when the narrow lines disappeared, if they disappeared. Okay. And finally, another way to have an idea of the progenitor is by analyzing the late phase in the spectra. By looking the lines, the profiles, you can have an idea of how was the explosion, so the geometry, if it was asymmetric, it was centered. You can also have an idea of the composition of the star before it dies. And doing this analysis, found in 2018, found that the progenitors of type 2 and 1B are very similar. It's consistent with previous results that I just mentioned. And that the progenitors of 1C are a bit more massive than type 2 is. This is a good way to constrain the progenitor mass and geometry of the explosion. The problem is that to have late time spectra, you need to wait a year, year and a half, and in a year and a half, the magnitude fades between 2 and 4 magnitudes. So when you want to take this, they are very faint and you don't have a spectra for all of them. So good analysis of these nebular phases are only done for nearby objects that you are sure that at late phases you can get it. So these are the ways that we have to study the objects. Now, what we care about this? Well, the thing is that the number of transients increases in the last year a lot. So here we have an example. In the last more or less 100 years, the first extragalactic supernovae was in 1885, more or less. Then the name supernovae was in 1934 by Zwicky here, that was coined. And then people start to look for new things in the photographic place, and things evolve. And you can see how things evolve when you change from photographic plates to the CCDs, how the number increases. This is up to 2010. This was a compilation that Mark Sullivan did. Now, in 2013, Mark Sullivan people knew that we have like new surveys coming soon. in 2013. That was the Dark Energy Survey. That was a camera in Chile, in the Blanco telescope. Then you have Gaia. Now we have many releases. The CTF, that was the evolution of IPTF, and IPTF was the evolution of PTF. Everything in Palomar in the US. LSST was already here. I didn't know, like many years in 2013, they already knew about this. And the expectation was that the number of transients will increase a lot. So how this changed? This was an updated plot in 2018 by Matt Stritzinger and Takashi Moriya. They are just like 5 years, but we can see an increase here in the numbers. The thing is, this plot just finished in 2018, but I went to the TNS, that is a transient name survey. So it's where we reported all candidates for supernovae, for all transients. And when we also report the supernovae, and I went back to the last 5 years. So you can see that from 2020, we are classifying around 2,200 supernovae per year. Now, this number is more or less small, it's very small. It's just the 10% of the transients that we are detecting. So you have here the numbers. We are detecting around 22,000 new transients per year. And this is up to 2024. This year, we will have more surveys, so these numbers will go up. Now, the thing is, we are classifying only 10%, but we are also classifying objects like AGNs, tidal disruption events, galaxies that they are doing weird things, or CVs, cataclysmic variables. So the classification of the number of reported objects is higher, but this is only for supernovae. And this is how it looks in the sky. This is from 2016, when the TNS started to operate. In blue, you have all reported transients, possible objects like to classify. And in red, you have all supernova we classify. As you can see, most of the objects we classify are in the north. And I was thinking why. And I think the reason is because of CTF. So CTF, they have a low resolution spectrograph in Palomar, and they are classifying everything that is brighter than 80.5. So they are doing like a very good job. Now, the quality of the spectra and classification, yeah, we need to go in details for that, but they are doing a good job in general. The thing is, this picture will change in a few years because most of the new facilities that are now building are in the south, and most of them are in Chile. So how that will affect, or how this is affecting the picture that we have about supernovae and transients, I will show you here. So you have in the y-axis the magnitude, so the luminosity of the object, and the characteristic time scale. Let's say before 2008, I put this number just, but before 2000, we only have like novae, very well studied novae, luminous ring novae, core collapse supernovae, 1/8. Some weird objects were there, but very few. How this changed? Now is the thing that we have. Now this is getting populated. So between the luminous nova and supernovae, we have these intermediate luminous transients that Andrea Pastorello in Padua is now working a lot on that. We also have long-lived core collapse supernovae. So these are core collapse supernovae that they may show some signs of interaction, and they stay longer for more than 2-3 years. So we have these extreme objects. We also have objects that they are even brighter than core collapse supernovae that we call superluminous supernova. So they are not luminous, they are superluminous supernova. We have here in very short time scale, characteristic time scale, some objects that they were called calcium rich. So objects that a few days after peak, they start to show these calcium lines. Now they changed the name. Now it's not calcium rich. They want to call it calcium strong because they don't know if the progenitor was rich in calcium, but they know the lines are strong. So they are changing this name. We also have the kilonova here from 2017 that will be the follow-up as part of PESTO. We have a region here where we have this false transient. This is very important because before all these surveys that I'm showing here, Atlas, CTF, Assassin, Panster, we didn't know about these fast transients. Because to have fast transients, you need a very good cadence. So you need a telescope that is scanning the sky very often because you want to know what is going on. So these objects are now like the hot topic in the field because they evolve very fast and some of them are very luminous that with the standard supernova mechanics, you cannot explain. So we don't know if they are supernovae or if they represent other type of explosion or event. So this is how is now more or less. And we know about this because of the facilities that scan the sky, but also because we are classifying objects. And here I showed some of the groups. There are many more groups, but I would say PESTO. If you go to the TNS and see what is the group that more classification have, is PESTO, IPESTO, PESTO Plus. So we are very good classifying objects. We also have the NUTS, the Not Unbiased Surveys. Leonardo and I, we are in these two collaborations. And you have people in Las Cumbres, POIS, that is in Chile. So this, as I said, is changing. So we have now here in the left, the surveys that are up to today. Atlas, CTF, Assassin. So with Atlas, it's even better because before was only in the north, was a telescope in Hawaii. But since last year, I think year and a half, they have also a telescope in Chile. So now they have the two hemispheres covered. And they have observations every 3-4 days. CTF in the north, Assassin north-south, Panstars in the north, Black Gem, so this started last year, I think, in La Silla, Go-To, north and south, started last year, and we are expecting these new collaborations. The first one, I think, that will arrive with Vera Rubin Observatory, that based on the expectations, they start operation May, June. That are the expectations after many delays. So we are waiting for that. We are also waiting for LS4, that is in La Silla, and SOX, that also have, probably you are familiar with SOX because Italians are leading this. So that also have many delays, but the expectations are that at the end of this year, November, operations are starting. And NTE, this is in the north, is in the NOT telescope in La Palma, but I don't know how this is going. I think in 27 was the expected date, but not sure. And Foremost, that is also in Chile. So this Foremost and SOX and NTE is to classify, while these ones are providing the lighthouse. So how this picture changed? This is the first slide, one of the first slides I show you. And this is what we have now. So we have now many new objects, very bright objects that have hydrogen, superluminous supernova type 2, but very bright objects that doesn't have hydrogen or helium, superluminous supernova type 1. Then we have some objects that show signs of interaction. So these narrow lines with a helium CSM, so we call YBN. Remember, the 1B is helium, so N, narrow lines of helium. And then the 1C, we have this interacting, no helium, no hydrogen, 1C. All these are interacting. Like 2 months ago, appeared a new object, a new type of object that they claim is coming from a very stripped star, that the ejecta is interacting with a silicon and sulfur rich environment, and they coin like 1EN. So they call it 1EN, and if you see, the D is missing. And it's because they expect that there is something that is not as stripped as this one, but is more stripped than the 1C. So they say, if this is following the onion-like structure, we will find this object at some time. Okay. This, now you see this is like more populated, so we have objects with these narrow lines, the type 2N, the 1BN, and here the 1BN, 1CN, and 1EN, everything with narrow lines and some specific elements marked there. But we also have some transitional objects, like this one that at the beginning was classified as a 1C broad line, so very broad lines, no helium, no hydrogen. But then after 100 days, more or less, the spectrum is dominated by hydrogen lines. So this is telling you that the star has a mass loss and then was expanding and found this CSR that was hydrogen rich. And that's why you have that. So all these things are giving us an idea about the life of the stars, but we still do statistical analysis to understand better what's going on. But it's not only the spectra that are changing, also the lighters. So here in the left, we have the hydrogen-rich supernovae. In gray, you have the plot that I showed before, the standard type 2s. I added 87A, that is a peculiar type 2, but I also add some extreme objects that appear. So we are having now objects that are very luminous and the time scales are larger. In the 1C, in the stripped envelope, we also have objects that are very bright. They evolve very fast or very slow, depending on the thing, but also double peak lighters. And interacting, we have a huge diversity, type 2Ns with short time scale, long time scale, and 1BNs that they always evolve fast. So just a brief summary, superluminous supernovae, superluminous. But how they are compared with the things that we know. So here we have the luminosity as a function of the day, so the light curve. We have the normal supernovae in red, and then we have the superluminous supernova population. So you see that they are very bright compared with the standard one, and the time scales are also longer. There is a huge diversity in the light curves of these objects. You have all kind of light curves with some peaks, some undulations, they go fast, they go slow. So you have all kind of diversity in the light curves. In the spectra, it's not as much as the light curves, but there is some diversity. And the thing is that you cannot explain this with the standard supernova mechanism. You need something else. And that's the things that we are doing. So we are trying to see which progenitor and explosion mechanism works for this type of supernovae. In some of them, that ones that you see that they are going up and down, you can claim interaction. So interaction is providing some extra energy to power the light curve. Or magnetar, this is one of the preferred things from people, the magnetar, that the magnetar is also giving you extra energy. One good thing, as I mentioned before, about the surveys are the double peak light curves. So before, you missed the first peak in some objects because you didn't have data for the good coverage. Now we have good data coverage and we are finding these double peak light curves, and they can tell you something about the progenitor star. For most of them, the first peak is attributed to the cooling, shock cooling, and the second one for the nickel, so it's powered by nickel, but in some objects it's not working, so multiple explanations are coming here. And we have the supernova precursors. So here I'm showing a paper about type 2s, because this was one of the few type 2s, just hydrogen-rich with a precursor, but the precursors started in 2005, 2007 with type 2N supernovae. So that ones that show interaction at the beginning. And the father of precursors, let's say, is Andrea Pastorello. He was studying these kind of objects that show like a first peak and then a main peak, and people were like, okay, what is going on? And the thing is, the main peak is the supernovae, and before the supernova explode, we have solar activity. So this is the precursor. This kind of analysis can give you an idea of the mass lost before the explosion, few years before the explosion. And that's important because we want to understand what is going on. But this is, you can do this kind of analysis very well together with the spectra. So in type 2s, again, you don't expect to see these narrow lines only for type 2s, but we are finding now that many type 2s, they have these narrow lines at early phases. So that means that they have like the ejecta interacts with a CSN nearby. That means that this CSN was a mass loss before the explosion and is very confined. So these narrow lines, in most cases, let's say, or at least the cases here, they last for 10 days. So after 10 days, you don't see the narrow lines. Of course, it depends on the configuration. If you have a more extended CSN or more dense CSN, it will be longer. So this is telling you about the CSN interaction, the mass loss. And this is the last thing about that. That, as I showed before, we are finding these extreme objects. So in this case, all of them are type 2, so hydrogen rich. In the case of IPTF14 HNLS, normal spectra. But when you look the line curve, that's not normal. That's not the thing that you expect for a type 2. You have multiple peaks. Right now, we don't know what is going on. A non-model works for this, so they try magnetar, pulsational instability, CSN interaction is one that fits good, but the problem is that you don't see the signatures of interaction in the spectra, so we don't know what is going on, and people are still working on this. If you look in ADLs, you will find more than 20, 30 papers just for this object, trying to understand what is going on. Then we have Ogle 2014 Supernovae 73. This is the green one here, looks like 87A, like the shape, but it's more luminous and is broader, the light curve. So in this paper from Giacomo Terreran, they explored different alternatives. One of them was per instability, but well, we don't know where it's going. And here in this paper, this object, the 16C3 CJE, shows the opposite of that. Very low luminosity, very narrow lines, double peak light curve, and you cannot explain this only with the standard supernova mechanism, explosion mechanism. You need to claim something else. So for these all objects that are not following the things that you expect for type 2, we need to claim some extra source of energy. But one thing they have in common, at least the type 2s I show, is that they are exploded in metal-poor environments. So these are some examples of the galaxy, of the places where they are. Even if there is a big galaxy, they are like far. So because of metallicity gradient, the metallicity is low. And to solve this problem, and I work mostly in type 2s, I started the follow-up of type 2s in low metallicity host galaxies. When I say low metallicity, is galaxies with metallicity lower than minus 18.5, that is the Large Magellanic Cloud metallicity, more or less. So here in the right, you can see an histogram of the type 2s. This is the luminosity of the host. So for these type 2s that we have for the last 30 years, most of them were in big galaxies, luminous galaxies, and that makes sense because before the surveys started, people were pointing to big galaxies because the probability to have a supernova is higher. You have more star formation, so they were just taking pictures of these big galaxies. But when the surveys started to scan the sky, we found many more objects in small galaxies. And taking advantage of that, in 2014, as part of PESTO, I started to follow type 2s in low luminosity hosts. Right now, we have more than 100 objects with a very nice follow-up, so nice spectral and photometric likers. And here, there is an example of few objects located in this low metallicity, low luminosity host. There are only 47 because in some of them, you don't see the host. So we need deeper images to see if there is a host there or what is going on. So from this one, as I said, there are more than 100. These are some of the works that we have published the last years based on these objects, where you have like this 15BS that we claim a more massive progenitor. So maybe at low metallicity, you have more massive red supergiant stars. So this claim that we did more or less there. Also, you have these objects that shows like a peculiar evolution late, and this suggests that was in a binary system, or just showing interaction just in the light, not in the spectra, peculiarities in the Lycor, like these short plateaus, very short, like 20 days. So all these are part of this low luminosity sample, and it's telling you that something is going on that we don't know, and that's the thing I want to explore. So I want to understand why. So if we have this huge diversity, it's because of metallicity, or there is another thing there. But the thing is that the lack of supernovae is not only for the type 2s, is in general. So this is the histogram of the host magnitudes for the different supernova types. And we see that most of them, well, as I said, they were selected in the galaxy, so it makes sense. But even though this is up to last year, November, I did it, there are very few here. So what is going on? What is happening there? They explode. How they explode? They don't. They just go and collapse. They explode, but they are very faint. So we need to explore what is happening here. And this is good because with the beta Rubin, we will go to higher redshift. And in higher redshift, we have lower metallicities. So we'll see what is happening there. So yes, to summarize, so core collapse, they show a huge diversity in the photometric parameters, in the spectral parameters. And now with these wide field surveys, even we are finding even more strange things that we need to explain. And we are trying to constrain the progenitor and the explosion by different approaches. But let's say the conclusion that we are sure is type 2 supernovae, the progenitors are red supergiant in most cases. I didn't mention, but 87A, well, it's a peculiar. It's not coming from a red supergiant, it's coming from a blue supergiant because of the peculiarity of the Lycor, so that was the conclusion. Type 2Bs, probably from a yellow supergiant, maybe in binary system. The question is, how many of them? All of them? So how this works and what is the difference in the Lycor and spectra? For 1B, only with one object, we said they have blue progenitors, but we don't know much about it. From 1C, the idea is they are very massive progenitors, but we don't know if they are in binary systems or not. For type 2Ns, we don't know anything. So we know they, Leonardo knows more than me because he's studying that, but we know they lose mass, maybe LBB stars, but we don't know. So we can constrain the properties with observations at early time. You will have an idea of the mass loss and the radius of the progenitor, but also at late phase, you can have an idea of the mass of the progenitor. So what we can do to make a progress? So start with statistical analysis. We have a lot of data. We don't need more data. I stopped to ask for data because I have a lot of data that is all the time looking at me like, use me. But we need to do this statistical analysis, combining all this to understand the general picture of core collapse supernovae. Grazie.
Do we have any questions here or online?
Give two very nice questions, stupid maybe. Just one is, we know that binarity, the presence of binary system is a common behavior in stars, and actually the function of binary system increasing with the mass of the component. Right? So the question is, I have never understood when you observe a supernova element with binary system, there is a star, the main component that explodes, you have the secondary one, something that maybe is also a massive star as well. What is the impact of the presence of a component on the feature that you observe on the exploded component? Say on the spectrum, for instance. Because if you have another massive star, it is also losing star due to its loss, so also there is something related to the binary interaction. You have some mass that is also related to the presence of components, some specific chemical composition. How this impact your interpretation of the spectrum, and so how this impact in this classification or difficulty in classifying this object?
Okay, so I think when you have a binary and the main star explodes, the general idea is that this one is the off. But let's say it's not that nearby and it doesn't affect that much. So we were trying like 2-3 years ago to find evidence of a companion by looking at the light curve. So the thing is, you expect that the light curve follows the cobalt decay. But our idea was look at the decay and see if you have some bump there that maybe is the contribution from the companion. Now this is difficult to do because of if the supernova is interactive, the bump is because of interaction, but also because it could create a magnetar, and the magnetar can also power the light. So it's very difficult to know what is the influence of the companion, if have any, in the property that we are looking at.
I don't know there is this big debate about the fact that there is a dependence on metallicity of products that you purchase. So the question is, have you found any evidence of increase of the diversity with the metallicity? Or you can say something, maybe you are there's not enough statistics.
Yeah, well, at least for type 2s, the hydrogen rich, if you go to low metallicity, the things we are finding are like more extreme supernovae, either brighter with a slow evolution, or the slow evolution is that they have the spectrum the same for many months without the changes. That's the thing I'm finding. Now the thing is that this effect is even stronger if you go to lower metallicities. So there is a region of metallicity that they are more or less similar to the things that we have right now, but if you go very low, you are finding peculiarities. Now the thing is observation, because I also asked for observation from the whole galaxy to compare, to have a precise value of the metallicity and how rich is the environment, and the observations will finish like in March, and then I can start to do the comparison between the host properties and the properties of the supernova. But in the things that I saw from this sample, if it's lower metallicity, they have peculiarities that you cannot explain with the standard.
I imagine that this is related also to the fact that the metallicity or massive stars are easily that target metallicity. So, in some sense, you can correlate the diversity with the.
Yes, and also based on stellar evolution, at low metallicity, it's easier to have the companion nearby because you have less mass loss, so it's affecting less the companion. There. So could be that the effect of the companion is more significant at low metallicity. So we need to explore that. Now, how we can distinguish if it's a companion or if it's a metallicity, that's the problem that Claudia from the future needs to figure out. For now, I'm just looking in the data, yeah. But that's the difficult part, because we don't know. So right now, we don't have a tool to say, okay, this is because of the companion. We're not sure.
Sorry, this is another question. In the very few cases for which you have a frame before the explosion and after the explosion, there is no possibility to compare the luminosity level in order to understand if there is a companion or not.
No.
You have a very
Yeah.
few.
Yeah, so this is the thing, and this is like the level they have for PTF. And this is for the pan stars. So the thing is, if you stack the images, you go to the limiting and say, okay, maybe most of them have a precursor activity, but we don't see it because they are very faint. So they are doing that. Now, to know if they are because of the companion or because they are just losing mass, it's hard.
You showed one or two cases for which you have archive frames.
Yes, but it's because when they go to the late to confirm, they find like a small star there. They say, okay, this is nearby the location. We believe that maybe it's the companion.
So it is not possible to relate it.
Right now, I think it's not possible. Maybe with new instruments. Yeah.
For example, type 2B is that
There is a companion. Yeah, that's the thing.
because we sold the companion.
Is there is near, but there is debate that is the companion or is just the cluster. So it's difficult. But in Titus, there are two cases that they found a star that is next to that one, to the
It's
location.
associated with supernova. Because usually it is assumed that a kickoff during the explosion. But in 1A,
Depends. In 1A, they claim you can see the group band. You can see a bump in the anchor, and that is the interaction of the supernova on the outer
companion.
layers of the core.
The dark
And this is
phase.
one way to compare one scenario with another, like single degenerate, double
yes,
degenerate.
but the parents one assume that you pass the companion. No. I mean, it is very difficult. So my question
Yeah.
was
It is
exactly this. If it is
Yes,
possible.
the other thing is that supernova is so bright that even if there is a companion there, the
You
light
cannot
is
see it.
completely dominated by the planet.
For this reason, I asked if there is the possibility to correlate archive with
That's why we were looking at late phases.
yeah.
Because at late phases, you have like a few light from the supernovae, and you can see there is something there. Now the complication, as I say, is if it's a magnetar, it's destroying everything. If it's interaction, it's destroying everything because you're not sure.
Sorry, another next question. Why you state that type 1C are related to more mass projector? What
Because-
is the reason for this?
Because they are found closer to star forming region. So
That's the
yeah, this is one of the reasons. So if they are closer to star forming regions, it means that they were more massive progenitors and they didn't have time to move a bit far away. That is the case for Titus, for example. Even if they are in the star forming regions, they are a bit far of the main activity. And then if you go in to see how significant is that, so you have the 1Cs are very close, then 1Bs, 2Bs, and Titus. And 1As are there, far. But that is one of the reasons. And also, the other one is because you need efficient mass loss. Well, you need the metallicity, but also more massive stars tend to lose easily.
I mean,
That's the idea.
if the scenario is that normal second, this means that we are seeing something below the elliptic shell in massive stars. So more or less, massive stars exploding as type 2 supernovae or 1B, 1C, whatever you want, more or less have a core mass, an iron core mass, not lower than something, but not much larger than something.
Yes,
So,
but they can have like a small core mass, yes, small core mass, and if it's not binary, that is not telling you how was the external
Yeah.
part. So you know that the progenitor is not that massive, but the companion did the work, removing the outer layers.
one of the hypotheses is not only you are assuming also only mean to do mass.
No, it's also companion.
So
Yes,
also
yes.
kind of interaction. But
Yeah. Yeah, but the thing is, if that is happening, why we don't find normal 1C at low metallicity? But the thing is, we are finding 1C broad lines. So something is happening. So maybe they are in companion. Something is happening. The angular momentum is changing. They rotate very fast and they explode as 1C. But the standard 1Cs, there are very few at low metallicity. Very few. If you find 5, you find a lot.
This is in contrast con the fact that the logical is you find a massive object. So I mean,
Yeah, it's very difficult. Yes. But we need to explore low metallicity because all works are in solar metallicity or higher metallicity.
I was asking if there is one standard supernova. Is there one? No.
No,
No. Okay, that's true.
but you know that people were like sad when they realized that 87A was not the thing that they expected.
Yeah. Well, okay.
That's the definition of a
That's
standard.
it's a joke. So, and I have many questions, but I'll just ask one. I'm curious about that strange object, ZTF, HLF. I don't know if it's
14 HLS. This one.
yeah, PDF, that one. I mean, totally. Can you say so?
Yeah, so it was a very strange object and IEEC. So they went to archival images and they found that was like probably an outburst like in 1940 something, like 50, that something was in the location. So if it's a single star, it has a lot of mass loss episodes probably, and if we believe it's a very massive one, and it's the explosion is pulsational per instability, so it loses a lot of mass in different pulses, and maybe this is produced by that is interacting. Now the problem is that you don't see the interaction in the spectra. So that's why this object is like puzzle, because we don't know what is going on. There is some work that they try with magnetar and they fit, but it's difficult to fit. Well, they fit like the overall thing, but the peaks is too difficult. Yeah. So I remember in one talk, you say, okay, we can explain this object combining everything. So combining all possible mechanisms, you can explain that. That's a problem, but yeah.
or two different supernovas probably in the same direction.
But you will see here, no, in the spectra. We have one that we were like, oh, maybe there are two supernovae because one, we don't know what is going on.
Along the same line of
Yeah,
sight,
that's-
or two, meaning
Along the same
line?
slide.
Okay, that's good.
And there are two different peaks. There is a writing.
Yeah, and we don't know what happened before because we don't have. So we don't know when it exploded. But when you see the spectra didn't change for a year and a half. So it was the same all the time. So for example, here, this is a 99 EM and 24 days. This is the IPTF, 137 days after discovery, because this is after discovery. This is wrong, after discovery. Then we go for a Type 2, 160 days, it looks like that. And this one looks like that in 600 days. So, yeah. And again, we don't know what happened before. So now, Yair is trying to find more of these objects, but yeah. You need a lot of eyes looking what is going on.
This is there is an additional peak at 300 days.
Yeah,
Very slight.
yes, it looks like what's going on. Yes, and we missed because it was behind the sun, so yeah. Yeah. Okay,
I have a comment.
yeah. Online questions?
Okay. Yeah.
Poi ci penseremo next time.
Let's see.
I have a comment. It's a facility nearby which starts this type of science. You said that we classify 10% of the chance.
Well, this is, I'm not saying, the numbers. The numbers say
I
that.
don't say I don't agree. The numbers say that.
I'm just
Reporting.
reporting what the numbers show.
And you also showed a plot with the time scales of the evolution and the life.
This one.
This is, for example, the superluminous, we started to find superluminous supernova when we changed the different strategies in our cycle.
Yes.
Because supernovae are so slow and they
Yeah.
don't change the luminosity over time.
Yeah.
And so we simply didn't go after
Yeah.
them. So a change in strategy allowed us to discover
New things.
new things.
Yes.
So do you think we still have we still have an old approach to classifying? Because maybe we are not feeling this plot because we keep classifying sources in huge galaxies.
No, we are not doing that. Now in Pesto, we are going to everything that is in faint
But
galaxy.
still,
It's biased, of course. It's biased.
so maybe a change in strategy somehow.
Yeah, but how?
Because we don't need to necessarily do the huge telescopes or, like, for example, to find kilometers, one of the strategies is having Schmidt telescopes, which have huge fields of view.
Yes, that is go to and black gem.
Like this. We don't need a huge telescope.
Mhm.
So just a comment. I don't think you have an answer, but you already gave me an answer. No, we changed the strategy.
Yeah.
So
Yeah. Yeah, I don't know.
that's
And also, well, now, for example, with PTF, well, CTF, they are classifying everything that is greater than 18.5. So let's say, well, but they are doing. So let's say they are changing the strategy now. How satisfied you are with the results, that's another question. But
now, of course,
I think everything will change now with Beta, and when ELT is operating, we will be another. Yeah.
we also need to try classify objects with photometry.
Yes, you can do now for standard ones, but you need to understand what is going on with the peculiars. If you don't understand the peculiars, you cannot classify. We leave that. Yes.
Oh, no, there are no questions online.
Okay. Thank you very much.
Thank you again, Claudia.
Thank you.
And